All right, if we start with this, we have the cell. What we're trying to do is identify where things are happening and what has happened when we go through all of the different pathways we've been talking about. And so inside the cell, there's the cytosol, and inside the cytosol is an organelle. That is the mitochondria, and the mitochondria is the powerhouse of the cell, and that is correct. So, what is actually happening in the mitochondria? And what is happening inside the cytoplasm of the cell? We're going to identify those two places. Now, where in the world does glycolysis actually happen? We've talked about all 10 steps, but where in the world, or where in the cell does it happen? Well, it happens in the cytosol. And so when glucose begins its process of being degraded, we're going to start it in the cytosol. But the citric acid cycle occurs in the mitochondria. And so we've got to get all of the organic molecules from glycolysis into the mitochondria for all of the pathways to work together. And so glucose starts, and we get converted into other forms of energy because glucose has all of the energy in terms of potential energy in the bonds. Obviously, we're going to make some ATP. We're going to have pyruvate created. Then we're also going to make the energy molecule NADH. So ATP, the actual molecule that we think of as energy, and then we make some NADH. Now, I asked the question in class, how many NADHs were made, and not a lot of people could answer that question. So probably something you really would need to look up, but we do make 2-pyruvate. Now, that pyruvate has to be moved into the mitochondria. And once it moves into the mitochondria, that's where we can begin the pyruvate dehydrogenase complex reaction, in which the pyruvate is converted into acetyl-CoA and an NADH, so one more energy molecule that will be formed inside the mitochondria. As we go through the citric acid cycle, what are the actual molecules of energy that are produced there? Well, obviously, in one step, we produced a molecule of energy that we know is actually GTP, which we know is an equivalent of ATP, because anytime GTP is made, it can transfer its phosphate to NADP to make ATP and GDP, and that costs no energy. We also created FADH2, and that is an energy molecule. It's an electron carrier. And then we made a whole lot of NADH in that process. And so the NADH is created. Now remember, the overall process for the creation of energy is the oxidation of a hydrocarbon, something that has hydrogens, carbons, and oxygens added to oxygen. You produce two things, CO2 and water. And so as we go through the process, the last thing that's produced is energy. And if we burn something, the energy is in the form of heat. We're going to be transforming the energy into something else here in terms of eventually the ATP. Now, where's the CO2 produced? The CO2 produced is in the citric acid cycle and the pyruvate dehydrogenase complex, and so CO2 is made. Well, where's the energy? Well, we had some energy that are produced in glycolysis with the ATPs, the NADHs, but we've also produced energy as equivalent of ATP, FADH2, and NAD inside the mitochondria. Now, we've got to get all of these things inside the mitochondria so that we can process this. But really, the ATP needs to be moved from the mitochondria into the cytosol, because that's where all of the energy is going to be utilized. It's going to be utilized in the cytosol. All the electron carriers have to be processed inside the mitochondria. Now, most of them are created inside the mitochondria, but there's some created outside the mitochondria in the wrong compartment. So we're going to have to get that in. And so we're going to have a consequence for that in just a moment. And we'll see that throughout this chapter. Again, ultimately, ATP needs to be in the cytosol. And we're going to make sure that we're going to transfer that ATP into the cytosol when we need it. Potential energy molecules that we have, and really what we're going to do is take the electron carriers, and we're going to go through what's called oxidative phosphorylation or the electron transport chain. It's a redox process, and we're going to extract the energies that those electrons represent that are being carried by NADH and FADH2, and that energy is going to be able to add a phosphate to NADP to make ATP. It's going to transfer it to ADP. Now, what we're going to do is ultimately place the electrons into oxygen, which forms the water. That's the last component of the oxidation of a hydrocarbon. And here's where we form water. We're going to throw electrons at oxygen. Oxygen loves to take those electrons. It will become negative, and as it becomes more negative, it will pick up protons until we produce water. Now, this is the major source of where we produce ATPs in aerobic oxidation, meaning that you need oxygen. We have to breathe that in. We're going to make 26 out of the maximum number of ATP molecules that we can make. Now, in older textbooks, or even I've seen in human anatomy and physiology textbooks, 36 is the old number of ATPs that can be formed. That's been readjusted. The maximum number of ATPs that can be formed from one glucose is 32, although we're going to look and see that more often than not, 30 ATPs will be made rather than 32 for most tissues. And so 32 will be the maximum, and 30 will be the one that is most often seen. Now, when we talk about the mitochondria, we have several things to talk about in its structure. There is an outer membrane, which has large pores, large holes in which small molecules and inorganic material can flow in and out. There's an inner mitochondrial membrane that actually has a lot of surface area with its folding, because the majority of things that happen actually happen inside the lipid bilayer, and we need more membranes so that we have the lipid bilayer to diffuse through, and the proteins that are going to process the reactions that we're going to see are actually embedded in those membranes. Now, there will be times in which the electron carriers will be floating in an aqueous solution, and that could be inside the matrix of the mitochondria, but sometimes it's flowing through proteins inside those lipid bilayers, and then sometimes it's going to be carried inside the membrane itself in carriers, and so very hydrophobic carriers that can have those electrons inside of them. And so what you're doing is, where the lipid portions that are making the membrane, where we have those tails that are moving in constant motion, we actually have small molecules that are roaming through those to actually move electrons around. I said that the mitochondria, the outer membrane has a large pores. They are actually, those holes are created by a very large protein called porin. It's a transmembrane protein, and what you can see, this transmembrane protein actually has a very large hole that is polar, that can stabilize things moving in and out. Now, the mitochondria has two faces in terms of the matrix side on the inside and the cytosolic face, or what we call the inner membrane. It can move through those pores, and each of those sides has a polarity. One is the in side, and one is the p side, the negative side, or the positive side. And we're going to have a differential in the number of protons. And so we have more protons on the outside of the mitochondria and less protons on the inside or in the matrix. So if you have a differential, more positives on the inside, that means more positive on the outside means the negative side is inside. We just have less positives, making it effectively more negative. And so that concentration difference is important because the energy will be converted into this gradient. And so there is two very separate processes that are going on. As we move the electrons from the carriers in the citric acid cycle and glycolysis through these proteins, we're going to end up putting those electrons into oxygen, and as a consequence, protons will actually be moved from the inside to the outside. It creates an electrochemical gradient. That is the end of one of the processes that occur with oxidative phosphorylation. And separate to that, this proton gradient, which has potential energy, is used for the synthetic process, which is totally distinct and separate. And so there is a protein called ATP synthase, which allows the protons to flow back through the membrane so that we can actually create ATP. What was interesting about the ATP synthase at first, when it was first identified, actually it was misidentified as a proton pump, in which protons would be pushed against a gradient with a breakdown of ATP. And that's what happened experimentally inside the test tube, although this was not what was happening inside cells. Now, why in the world would this be able to run in reverse? A student answered, well, given reactants and products, you can force reactions to go backwards, and that is absolutely true. The one thing about an enzyme is that it stabilizes a transition state. The transition state of breaking an ATP into the phosphate and the ADP, or the diphosphate, is exactly the same transition state as putting those two together. So the enzyme is going to manage to facilitate both reactions. Now, when we think about this process as being a redox reaction, then we can think about the electrochemistry behind it. And there is an equation that you learn in GChem 2 about calculating the amount of energy there is in the flow of electrons if you take into account how many electrons there are, a constant number, and how different the electron potentials between the two entities that you're transferring electrons from and to. Now, in this process, NAD and FADH2 yield 2 electrons. It's a 2-electron carrier. So when you do this calculation with most things, it's 2 electrons. This is the N value, which is something that most people miss, especially on exams. And so make sure you bring your calculator for the exam. Now, the Faraday's constant is something I will give you, and it's a value in energy per mole that you're going to move, which is also related to the voltage difference, and then the delta E is in the voltage depending upon what you use to do the reaction, and so that's dependent upon the two entities. As a very simple example, if we have fumarate plus 2 protons plus 2 electrons yields succinate, and the NAD plus a proton plus 2 electrons equals NADH, we can look at that reaction and we can see the electropotential difference between those two values and with this reaction. If you take a look at that, we can plug that into the equation, and you can see that this particular reaction doesn't seem to want to go too well. It is a positive value, but this is the kind of calculation that you'll need to be able to perform on the exam. Taking it from a example problem to something that might be important to us. I told you we're going to take those electron carriers and we're going to take the electrons and give them to oxygen to produce water. Now, if we take that amount of electron volt differential, we can see that that's a very large difference in electron potential. And so when we do the calculation here, we are going to see that we could create a very large number in terms of energy, minus 52.6 kcals per mole. Now, that number doesn't seem to be very large at this moment in time. And remember, we convert between kcals and kilojoules quite often, but 52.6 kcals per mole, let's compare it to a very energetic molecule, the breakdown of ATP, which will give off or require 7.3 kcals per mole to actually make. And that is the process of ADP plus PI to make ATP is equal to 7.3 kcals per mole. If you look at 52.6 in that respect, if you actually do the calculation itself, and we take 52.6, divide it by, and it's not kilojoules, I'm sorry, it's kcals. And we'll go back and correct that to kcals, which is a nutritional calorie actually, per mole. We will see that we can calculate that, and if someone actually gets their calculator out, we can actually get that particular value, and that particular value becomes, mathematically, someone do that. And what did you get with your calculator? 7.21. We could make potentially 7.21 ATPs for that amount of energy. Unfortunately, we're not going to be able to yield that. An NADH will allow us to yield only 2.5 ATPs per NADH. That's only 34.7% efficiency. Now, what you've got to think about this is that electrons must move through many different players. If by chance I had an enzyme to make it directly go to oxygen, I extract that much energy, but I don't. I have to go through many players, and every time an electron moves from one entity to the next, it has to go down the energy value. And so I move the electrons from place to place to place to place to place. Each time I lose some energy, and in some of those cases, I will actually pump protons through a protein to actually convert the energy before it gets to ATP into a gradient. And so even though I do not extract 100% of the energy, I can convert the energy not into heat, which I can convert a lot of heat in this process, but I can convert it into a method or into a storage amount in that gradient, which then can be converted into the bond energy of the ATP. Now, to take all of these electrons and get this type of energy process, we have to move the electrons from a carrier to a carrier to a carrier. And there are a number of different things, entities that will carry electrons. We're also moving electrons through proteins, and so I have to move it through that particular protein, and within the protein they're fairly large entities, so there are multiple places in which the electron has to move from one place to the next to the next to the next. And so we're going to see this process occur, but we need to know what kind of carriers or where the electrons can actually be held. Some of the carriers are going to be in the membrane itself, and some of the carriers are going to be in an aqueous environment. One of the largest examples, or the first players that we're going to look at, is a molecule or organic structure that is termed Q. Q stands for ubiquinone, and what you can see is there's an organic ring, and organic rings can hold electrons. And Q is the fully oxidized version. QH2 represents the reduced version. It has the 2 electrons, plus it picks up protons. In essence, it will pick up the hydride and then pick up a proton, very similarly as FAD does. And it will carry those electrons. In the fat layer. Now, if you take a look at it, that's two hydroxides. That seems to be fairly polar, but this molecule is not polar at all because of this repeating unit. That unit is 10 units long, and so if you think about that, that is a very, very long hydrophobic tail. It is so hydrophobic it overwhelms even the hydroxides, allowing it to be hydrophobic enough to be in the membrane. The next carrier can be familiar to you. One of them is the FMN molecule. It's the organic ring structure that is actually the component that FAD actually holds the electrons in. And remember, the electrons can come as a hydride, attack the nitrogen, move the electrons around, and creating a negative charge on the opposite nitrogen, which then picks up the proton. But this organic structure is now going to be embedded in some of these proteins and be able to carry those electrons and transfer them. Another carrier that might be familiar to you, the structure, is a porphyrin ring that has an iron in the center. And we've seen this porphyrin ring in the protein called hemoglobin. And at that point, the hemoglobin, the iron, was there to bind to oxygen. But in this case, the iron is going to be in a protein called cytochrome C, and it will be able to carry an electron. And what will happen is the iron will change from a +2 state to a +3 state, and it's a 1 electron carrier. Now, what we're going to have is sometimes 2 electron carriers, sometimes 1 electron carrier. That's going to create some situations for us that we're going to have to deal with, and it gets a little complex, but we'll follow that through when we get there. But we have both 1 and 2 electron carriers. Another items that can carry electrons are metal centers. Copper can change from a +1 to a +2 state, and so we can carry 1 electron in that. We also have iron that is bound to sulfur in what are called iron-sulfur clusters, and sometimes we have them coordinated to the sulfur of cysteines, so the irons are held in place in coordinated zones between cysteines, and so a Fe2S2 can carry more than 1 electron. Fe4S4 complexes can carry lots of electrons, and so we can have single electron transfers or multiple electron transfers in irons that are not heme. And so these complexes are found on a lot of different places. Now remember, there are 2 separate and distinct events: an oxidative phosphorylation, pumping out of the proteins into the matrix, and we get a proton gradient. The energy is converted from the electron carriers into that gradient, and then we have the electrons that flow back through the synthase for ATP synthesis. They are 2 separate and distinct. Now, when we started to identify what was happening, we looked at the mitochondria and we isolated different things out of the membrane, and actually they were different proteins. And so how in the world do we isolate things out of the mitochondria? Well, the first step is to isolate the actual mitochondria themselves, and we have a separation technique that is able to isolate organelles. And if you remember back, what we looked at previously in other courses was that we can use ultracentrifugation to separate very large items like organelles, so you can separate out the nucleus and the mitochondria away from each other, and other of the different organelles. And then what we can do is, once we have a purified fraction of mitochondria, break that membrane and isolate different fractions, different proteins from that. In that case, we actually discovered, once we separated the 4 or 5, it was actually 5 different fractions of different types of proteins that were at large concentration, and different reactions that occurred. The different fractions then could take the NADH and transfer it to the organic molecule Q. And so in some ways, those particular electrons went from a carrier into Q. The second fraction that we found actually took succinate and converted the electrons that were in succinate all the way into Q. The third fraction, we're going to call them complexes, took Q and then allowed the electrons to be moved into cytochrome C. The fourth fraction took the electrons from cytochrome C and actually reacted them with oxygen, and the electrons ended up into or forming water. And in the last fraction, we actually found a ATPase enzyme that breaks down ATP, and we believed, again, remember, we believed that it was a proton pump. This was very similar to other proton pumps in structure and in function, but after looking at it, we discovered that it was the exact opposite. The protons moving down a gradient could actually synthesize ATP. Now, depending upon what textbook you're going to use, they will always use complex 1, 2, 3, and 4 as this description of what's happening in these proteins. But what you're going to find is the name of these complexes will be very different amongst different textbooks, sometimes between different standardized tests, sometimes even in the literature. And so if you want to be very formal, you talk about what the electron carrier begins and where it ends, and give it a generalized class of enzyme, like in this case complex 1 and 3. But in complex 2 and 4, the way this book actually names them is a little bit more of the common names of succinate dehydrogenase, cytochrome C oxidase, and so it really depends. If you learn these names verbatim, and that's how you memorize them, you may be fooled on an exam or on test bank questions or on the standardized exam or going between two books. But if you understand the process of what is happening, you may not be fooled by a simple change in the name. Now, what was important was complex 1, complex 3, and complex 4 pumped out protons from the matrix to the intermembrane space. And so this is an important distinction among these particular complexes. They will work in conjunction to actually synthesize ATP eventually. Now, as we look at the flow of electrons, NADH will be able to synthesize 2.5 ATPs, while FADH2 can only synthesize 1.5 ATPs. So when you look at these pathways, you see NAD flows through certain proteins and FADH2 flows through certain proteins. What do you identify as the differences? Now I'm going to put a little star by NAD because most of the time it's going to produce 2.5 ATPs. We're going to find a case where that might not always be true, but if you were talking about NADHs that are produced in the matrix, always 2.5 ATPs. The three proteins that we're going to use is in the NADH case is complex numbered 1, 3, and 4. And with the FADH2, we use different proteins. We're going to use which ones that are different. If you take a look, 2, 3, and 4, and so that's a difference between the two. What else do you find that is different between those two entities and those pathways? What is the difference between the top and the bottom, where we're using FADH2 or NADH to process what's going on? Okay, one of the differences that you see is that FAD might be coming from the intermembrane space, not the mitochondria, not in the matrix of the mitochondria, and so electrons might be flowing from outside the matrix, and that's a little bit different. Now the NADH in the top is actually coming from the matrix, but that FAD that is identified at the top is coming from the inner membrane space, or the cytosol. This is something that we're going to look at. If you take a look at this, the succinate actually to fumarate, well, really, that is the enzyme that is in the citric acid cycle. And so FAD coming from there is the traditional one. Now, what we didn't teach you, and we will teach you later, but fats also will produce FADH2, and so there's an entrance of FAD from fat degradation into this chain. We're not looking at that at this moment particularly, but you need to understand that we're going to come back and identify that. But if I actually go back to complex 2, when people were working on that particular protein, they discovered it in the citric acid cycle and they classified it in that way. But they also identified it in the oxidative phosphorylation, and they studied it that way. And it wasn't until later that in comparison, they discovered it was the exact same molecule. And so that particular enzyme is both a citric acid cycle enzyme that you've already learned, and now it is part of the oxidative phosphorylation. And the electrons will then be taken from the FADH2, and it will be placed into Q through what we call complex 2. If you actually go back and look at the name from this book, they actually name it the citric cycle acid, or the citric acid cycle intermediates enzyme name. Is there any other difference that you see in these particular processes? Go ahead and look. What do you see that's different? If we look at the stoichiometries of how many protons are pumped, okay, do you see a difference between that? Yes. In the NADH, 10 protons are pumped across the membrane. In the case of the FADH2, 6 protons are pumped across the membrane. This is going to be important. We're going to come back to this. In particular, we're going to take a look. What we need are protons in the inner membrane space pumped away from the matrix, so that we have a larger concentration on the outside to allow it to flow back in. Now, when we take a look at a proton gradient, okay, there are two things that can create the gradient. One is actually moving them from one space to the other, from the matrix to the inner membrane space. That creates a gradient. But do you see any other place that will either work towards making a gradient differential larger, or do you see any place in this process that might work against a gradient, make the gradient smaller? There are two examples between the two processes in which we find either making more or fighting against it. Here, in the process of creating water, we actually take free protons and combine them to oxygen. That makes lower concentrations of free protons in the matrix. That creates a gradient, a differential, and that is part of the rationale of why we can actually have synthesis. The more different we have across those membranes, the larger the energy. And so when we take those protons and combine them to oxygen, we create less protons on the inside, creating a larger difference. Now, if you take a look anywhere else, do you see anything else that might fight against proton gradient or the differential from being formed? Next time, we're going to look at one more place in which the gradient is actually increased in this reaction.